Hello, good morning everyone. Can you hear me?
Yes, sir.
Oh. Okay, so till last class, what we have discussed is the corrections which are arising from relativistic effect and spin orbit coupling, which are related to the fine structure spectra of hydrogen atom. So we explained the origin, that is the mechanism, and what will be the final correction, that means the energy term that will be added or subtracted from the original unperturbed energy value. We have seen there are basically two different terms. One is coming from this relativistic effect, another is coming from the spin orbit coupling, which will be added towards the energy level, that is the Bohr energy level for hydrogen atom. Okay, we have ended up with this expression E n j will be equal to minus 13.6 divided by n square, and within the bracket we have 1 plus alpha square by n square. Again within the bracket we have n divided by j plus half minus 3 by 4, and so that is equation number 6.67 what we have got until yesterday. Okay. So now today we will discuss the consequences of this thing. So as I mentioned earlier, that these fine structures are part of the spectra which are commonly not observed in standard spectrometers. That means whenever, let's say, if the source of the spectrum is hydrogen atom or one electron atom, so for simplicity for the moment, let's assume hydrogen atom. And if we want to see what sort of spectra are arising as a result of transition between different energy levels, then most likely or primarily we will be observing those series which lie in this Balmer series or Passon series. So those spectral lines which lie in the visible, ultraviolet or IR regions, that which I explained earlier. And if you remember that there are basically three primary series which are commonly observed. Now this fine structure spectra, as it is a correction added to the originally present, or let's say, or unperturbed energy level, which means that there will be some shift in the energy, or let's say the wavelength or the frequency of those spectral lines which we already discussed earlier. So now here we will first look at this quantity which is called as term shift. As you know that whenever there is a spectral transition, there will be some energy that will be associated with it. So let's quantify that by this term delta E. And if we divide it by h and c, so h is Planck's constant and c is the velocity of light in free space, then we can define this quantity delta T, which is called as term shift. So this is a very commonly used quantity in spectroscopy, and the unit is usually in centimeter inverse. So it usually says that how much is the shift that is coming up because of this particular correction from the unperturbed configuration. So we'll be using this term shift in order to find out the shift, let's say, in future lectures also, in the case of Zeeman effect or even subsequent effects also. So this is a common term which we'll be using throughout. And now what we will do now is that we'll use this equation 6.67, that is the equation which we have explained in the last slide. We'll use that to calculate the term shift from different interactions. So as we know that this unperturbed energy level can be expressed by this expression, that is En will be equal to minus 13.6 divided by n square, and the unit is in electron volt. Now for different values of J, different fine structures are observed. So that we have also discussed in the lecture yesterday, that for a particular value of n, there are several values of J that are possible. So let's say if it is n equal to 2, we can get two values of J. That means J equal to half and J equal to 3 by 2. Simultaneously, if we look at the level n equal to 3, then there are three possible values of J, which are J equal to 5 by 2, 3 by 2, and half. Okay. So this says that the fine structure splitting gives us additional energy levels which are characterized by the quantum number J. So now we'll look into this. What are the fine structure levels that are arising in this case? So let us first say if there is a transition from n equal to 3 to n equal to 2. So the corresponding spectral line is usually also denoted by H alpha line. Okay. Now here for n equal to 3, as you know, the possible values of L will be 0, 1 and 2. Why? Because the value of L will start from 0 to maximum of n minus 1, that is 2. So 0, 1, 2 are the allowed values of L for n equal to 3. And we can calculate the possible values of J for this case, which will be 5 by 2, 3 by 2 and half. I hope you can follow this thing, because J will be nothing other than L plus S to L minus S. So S is half here. Okay. So the maximum that will be possible will be 2 plus half, and the minimum that will be possible will be basically half here. Okay. So now if we look at n equal to 2, then the possible values of L will be 0 and 1, and you can also find out what will be the possible values of J here. So the values of J in this case will be 3 by 2 and half. So this you already have seen earlier. Now if we draw the energy level diagram for such specific case, then we will get something which will show it in the next slide. So here you can see there are several energy levels. So for example, n equal to 3 and n equal to 2, we have drawn the possible energy levels which are characterized by different terms. So the term symbol we have explained in the last class. So it is usually characterized by this convention: 2s plus 1 Lj. Now for different values of L, we will get these terms like S, P, D, F. So here, let's say for n equal to 3, if you look at the terms that we'll get is, so let us look at for n equal to 3, I have 3 different values of J which are possible. So I have drawn 3 different energy levels. So this is for J equal to 5 by 2, this one is for J equal to 3 by 2, and this is for J equal to half. Okay. And the corresponding values of terms, or let's say the terms which can be associated with these energy levels, are the following. So here 2d5 by 2 is the term which can be associated with this top energy level. Okay. So 3 is the value of n, which I am just putting it before it. Okay. And for J equal to 3 by 2, the terms which are possible will be 2p3 by 2 and 2d3 by 2. For J equal to half, the terms which are possible are half and 2p half. Similarly, for n equal to 2, the energy values will be characterized by the values of J, which are J equal to 3 by 2 and J equal to half. And the corresponding terms will be 2p3 by 2 for J equal to 3 by 2, and for J equal to half, the terms will be 2s half and 2p half. I hope this is clear, right? Is there any question up to this?
Hello, sir.
Yes.
Sir, in the top, why there is a 2D 3 by 2?
No. Can you tell me? Where? Here?
Yes, on the right. The line below that.
Okay, D3 by 2.
Yes, sir.
You're talking about this one, right?
Yes, sir.
Okay. So let's do one thing. For the moment, please ignore these terms because they have certain implications. I will explain it later. Okay. Okay. Is
Okay,
it?
sir. Okay, sir.
Okay. So just to clarify, for the moment, please ignore these second terms. 2d 3 by 2, 2p half, and 2p half here also. Okay, just please ignore all these three terms. So it is a very good question. This actually is coming up because of a certain effect. I will explain it later. For the moment, please ignore these three terms. Okay, just only consider these first terms which are mentioned here. Okay. So, okay, any other question now? So now I have n equal to 3 and n equal to 2. And the selection rule for transition in this particular case will be delta L equal to plus minus 1, delta J will be equal to 0 or plus minus 1. So as you know that in case of any atomic or spectroscopic transition, there have to be certain selection rules that determine what will be the allowed transitions and what will be forbidden transitions. So here also the selection rules are delta L equal to plus minus 1 and delta J will be 0 and plus minus 1. Now let us look at what are the transitions that are happening following these selection rules. So there is this line that is coming up from n equal to 3, j equal to half to n equal to 2, j equal to 3 by 2. The second line is from this one, that is j equal to 3 by 2, which is belonging to n equal to 3 to n equal to 2 and j equal to 3 by 2. And there is a third line that is coming from n equal to 3, j equal to 5 by 2 to the final level of n equal to 2, j equal to 3 by 2. And there are another two lines which are also possible under the selection rules. So one is from n equal to 3, j equal to half to n equal to 2, j equal to half, and n equal to 3, j equal to 3 by 2 to n equal to 2, j equal to half. Okay. So these first three lines, they are actually ending up at j equal to 3 by 2, n equal to 2, and the second two lines, they are ending up at n equal to 2, j equal to half. And they are basically the nomenclature that is used for these specific lines are given by these names 3a. So here actually I have drawn these vertical lines just to mimic whatever transitions are happening on the top, that means within the energy levels. Okay, so here I have 3a, 2a and 1a, and 3b and 2b. Okay. Okay, so why 3a? The name 3a is coming because this is 1, 2, 3. So that is the starting level, and a because this level is denoted by a here. Okay, and then 2a is because this is level 2 and this is a, this is level 1 and this is a. That is why this line is named as 1a. Similarly, for this particular line, the initial notation is 3 and here the final number notation is b. That is why this is termed as 3b and this one is 2b. So I have a total of 5 lines, and if I want to calculate what will be the value of term shift, then I can do that. The values will be 0.036 centimeter inverse between these two levels and 0.108 centimeter inverse between these two levels and 0.365 centimeter inverse between these two levels. That means n equal to 2 principal quantum number, j equal to 3 by 2 and j equal to half. Okay, so is there any question so far on this?
Is it possible for like the transition in the same end? Like for n equals to 3, for L equals to 2 to L equals to 1, like that. Is it possible?
No, can you repeat the question, please?
Sir, in n equals to 3, is it possible for the transition L equals to 2 to L equals to 1?
Within n equal to 3?
Yes, sir.
No, within the energy level, if you have a transition, then you will not see it, right?
Okay.
Okay, so I'll explain it. Okay, so let's just think of, okay, I think I need to, okay, so I'm getting out of, let me see if I have a whiteboard here. Do I have one? No, I don't have one. Okay, so let me just open another slide. Okay, so you see, whenever I'm talking about any kind of energy correction, so you need to first remember that let's say this is my n equal to 1, this is my n equal to 2, this is n equal to 3. Okay, these are the principal quantum numbers which we have got from the even let's say Bohr theory or even the Schrodinger equation solution, right? So there is En will be equal to minus 13.6 by n square eV. Okay, so that kind of tells us what will be the primary energy levels. These are something which we see. Now, if you remember that if there is a transition like this, or if there is a transition like this, or if there is any kind of transition like this, then I get certain spectral lines. Okay, you agree to this, right? Now, when
Yes,
I'm
sir.
talking about fine structure, these are a higher order correction to these energy levels, which means that I have certain En and I am adding certain delta E to this. Okay, so let's say this has a certain energy level, this has certain energy level, this has certain energy level. Okay, so now what this fine structure or any kind of correction is doing is that this is basically adding up some, let's say delta E, or here also let's say some delta E. Okay, that means some broadening is being introduced because of this. So what you can say is that let's say there is some certain width that is being put into place here. Okay. Same is true for here. So earlier, whatever transitions I was looking at, these are basically between this level and that level. There I didn't need to worry about what are the further splitting that are happening within the level itself. So now each of these levels are characterized by certain value of J, right? Okay. Now, what I am doing as a result of this fine structure is that I am also taking into account these finer levels that are specified by different values of J. Now keep in mind that whenever I am seeing any kind of spectra using a spectrometer, I will primarily see this spectrum, or let's say that particular line or that particular line. Why? Because the energy level, or let's say the intensity or the frequency that is associated with it, or let's say the number of atoms that are associated during this transition are much higher compared to any other kind of transitions that is happening within this tiny correction terms. You remember that we have calculated this delta E divided by E, and then we saw that this is typically coming either of the order of 10 to the minus 4 or 10 to the minus 5, something like that. Okay, so you can imagine that these corrections are very low in value, right? So what it means is that if I want to see a spectra, I have to first see these larger lines, and the corrections will be somewhere around it. Okay, so let's say if I see a big line, then the corrections will be somewhere around it. And if the resolution of my spectrometer is not good enough, I'll only see this one and this one. But if I have a very high resolution, then I can further resolve it, and then I can see probably there are 3 lines. Okay, so you have to keep in mind the primary transitions have to be between the n levels. So no spectra will appear between these two. Or let's say if there is a transition between these two levels, that will not be appearing here. So I will not be seeing that. Okay, so there have to be a larger transition here, and the subsequent transitions have to be associated with it. Is it clear?
Yes, sir.
Okay. So now I'll go back.
Sir,
Yes.
sir, why are some transitions happening between same values of L? So, sir, there are some transitions happening from S to S, 3S to 2S. So the selection rule will be violated, right?
You are saying which one? You tell me specifically.
Sir, the 3B line.
3B line. Right. Okay. You mean this one to this one, right?
Yes.
Okay.
Yes,
So
sir.
the thing is that, see, there are 2 sets of selection rules. So if it is following any one of them, the transition will be possible. So here, although the L is same, but if you look at the J value, that is basically, I think, changing, right? So delta J is 0 here, right?
Yes, sir. J
Okay,
is
so that
delta
is
J.
kind of allowed here. Okay.
Yes.
So now, so here are few lines which I have drawn already. Now, experimentally, what was observed is that the difference of the delta T, that means the spectral, sorry, what was the term? I said term shift. The term shift between 1A and 2B experimentally has been measured to be of the value that is 0.319 centimeter inverse, while the theoretically calculated value is 0.329 centimeter inverse. Similarly, between 2B and 3B, the value of term shift, which is experimentally measured, is 0.134 centimeter inverse, and the theoretically estimated value is 0.108 centimeter inverse. So you can see that there is some difference between the theoretically calculated and experimentally measured values. What is the reason behind this discrepancy? So there is some argument which have been given by these two scientists, Lamb and Rutherford. So they did the measurement through microwave spectroscopy and they saw that there is some discrepancy that is happening. So the reason is the following. So let's say if we have a specific value of n, so let's say there are two different sublevels or two different terms which are possible. Okay, so let's say 2p half and 2s half. So these are, I mean, they have same value of j, but also the spin value is also same, and the L value is different, which means that for a specific value of n, so okay, so 2p half and 2s half. Okay, so let us look at, sorry, what are the terms? 2p half and 2s half. Okay, so you see, there is, let's say, for n equal to 2, if I look at, then there are several values of L which are possible, which are L equal to 0, then L equal to 1, and L equal to 2. Now, for L equal to 0, if I want to calculate the value of J, then I'll get some value of J, which will be half. And for L equal to 1, the values of J which are possible is 3 by 2 and half. Similarly, for L equal to 2, the values of J which are possible is 5 by 2 and 3 by 2. Now, there is one thing to notice here is that the value of, let's say, J equal to 3 by 2 is coming from two different cases. So for L equal to 1, it is coming, and for L equal to 2, it is coming also. Similarly, for L equal to 0, I will get a J value of half, and that similar value of J is also coming from L equal to 1. Okay. So what it means is that although I am getting certain specific values of J corresponding to a particular value of n, which, for example, in this specific case are three different values. These are 5 by 2, 3 by 2, and half. But it is not necessary that this specific value of J is corresponding to one particular term symbol. Or in the other way, what I can say is that one particular value of J that does not necessarily corresponding to one particular energy level or one particular kind of, let's say, term, I think is a better alternative here. Okay, so simplistically, if I look at J equal to half, then J equal to half can appear from L equal to 1, let's say J equal to 3 by 2. So it can appear for L equal to 1 and L equal to 2. Similarly, for this case, n equal to 4, if I look at J equal to 5 by 2 can appear for L equal to 2 and L equal to 3. J equal to 3 by 2 can appear for L equal to 1 and L equal to 2, which means that one specific value of J, which I am using here to denote a particular fine structure level, can be originating from more than one spectroscopic term. Is this part clear?
Yes, sir.
Yes, sir.
So that is why there is some energy splitting which we are not considering. So some additional correction have to be done. So this kind of correction, or let's say the shift that is appearing because of this correction, is called as lamp shift. So physically, that there is a discrepancy between the experimentally measured value of term shift and theoretically calculated term shift, and that is appearing because of not considering this degeneracy, or let's say this discrepancy, and this shift is called as term shift. So this one actually I explained yesterday. So after the correction, so lamp correction, what actually it was done is that these energy levels are further actually redrawn into a different manner. So they are a little bit kind of splitted, and here you can see that there is basically how many. So earlier we had for n equal to 3, we had 3 levels, that is 5/2, 3/2, and half. Okay, and here we have basically 4 levels. So for example, there is this top level that is represented by d 5/2, then there is d 3/2 and p 3/2, and then there is s half and p half. Okay, so if you remember earlier, actually these s half and p half, they are into the same energy level, but as per Lamp's correction, they are not the same energy level. Rather, there is some delta t, or let's say term shift, that is present here. Similarly, for n equal to 2, earlier we had only 2 levels. So if you look at, there are 2p 3/2, 2s half, and 2p half. Here now, this 2s half and 2p half, they do not belong to the same level. Rather, there is some term shift that is also present here. So if we take into consideration all these things, then if we now calculate the term shift between I think 1a and 2b, and let's say 2b and 3b, then this correction matches with the experimental value. So there is a fine structure which I will be sharing with you. So if you are interested, you can actually read more on these things. So since this part of this syllabus only discusses qualitative discussion on these things, so I'll not get into too much details more than that. However, I'll share the file with you. If you're interested, you can read these things. Okay. Okay. So any question on this? And if you are also interested in knowing the mathematical details, then anytime you can go and read this golden book by Brunstone and Jochen. So this is, let's say, the mother of atomic physics, this book. So if anyone is interested in pursuing atomic physics, or is interested in this subject, please start reading this book as soon as possible. So if you read this book, everything is there already. Okay, so now as we say that if there is a correction, that means that the spectral line will not be a single, it will not be designated by one specific frequency. So there will be certain width which will be associated as a result of this correction. How do we know this thing? So we can use the uncertainty principle to calculate this. So as I say here, that if there is this unperturbed level which I represent by a single line, then after the correction I will get a certain broadening. And if I want to calculate this, then I will use the uncertainty principle, which is delta E dot delta T of the order of h bar. Now E we can write equal to h times nu. So h is the Planck's constant, nu is the frequency, and I can write delta E equals to h times delta nu. Okay. Now let's say tau is the lifetime of one particular state. So if that is the case, then using this expression of uncertainty principle, and if I substitute these values, then I can write h times delta nu times delta t will be of the order of h bar, or delta nu dot delta t will be of the order of 1/2 pi. So here delta nu will be of the order of 1/2 pi times tau, or let's say delta nu will be inversely proportional to the lifetime of the state. Now typically if within the optical transitions, the lifetime of a state will be of the order of 10 to the power minus 8 seconds. So this is the typical lifetime. And if we want, we can calculate the value of corresponding delta nu, which is associated with this. So we'll simply plug in this value, and the value of delta nu we get is of the order of 10 to the power 7 second inverse. Okay. Now let's say if we take another example of visible light, and let's say the incoming radiation has a wavelength of 600 nanometer, then the question comes, can we calculate the delta lambda? So can you try to do this? The answer is written here. You can actually try to do the calculation.
So,
Yes.
so how do we find out the lifetime value, or is it a experimental thing?
So there are ways to calculate. You first do this calculation, calculate delta lambda. Anyone got the answer? Okay. If you have not, then you try it at home.
Sir?
Okay. So the answer
sir.
will be 1.2 times. Yes.
Yes, sir. So the 1.2 into 10 to the power minus 14. This is what I got.
What is the unit?
Meter.
Okay, check it if it is the correct one, because it says 10 to the
Yeah,
minus
yeah.
15 meter.
So, sir,
Okay.
my answer
So-
is 1.2 into 10 to the power minus 14.
Meter.
Yes, sir.
Okay. So here, what I have here is 1.2 times 10 to the minus 4 angstrom. So now, if I, so you do, whoever has not done it yet, you do it at home. So now here, if you see that the lambda here is of the order of 6,000 angstrom, and delta lambda is of the order of 10 to the power minus 4 angstrom. So effectively, if I take the ratio between these two, then the ratio come out to be of the order of 10 to the power minus 8, which means that, let's say, in the experimental condition, if I want to write what is the correct value of lambda, then I'll write in this form, lambda plus minus delta lambda, which will be 6,000 plus minus 10 to the power minus 4 angstrom. So as you see that this value is quite small, because this is almost 10 to the power minus 8 times, which means that this correction, or let's say the change in lambda, or let's say if there is a spectral line which has a wavelength of lambda plus delta lambda, or let's say lambda minus delta lambda, then they are too small to be detected using ordinary spectrometer. So that is why we usually don't see these corrections, because the value of this correction is very, very small. Okay. And here actually on the left hand side, how to do the earlier calculation is given. So all you have to use is this formula, lambda will be equal to c by nu, and then you take the derivative, you will get this. Okay. So is this part clear, what I said?
Yes,
Yes, sir.
Yes, sir.
Okay. So now coming back to the question of measurement lifetime. So you see, the first part is that lifetime is inversely proportional to delta nu. Okay, and delta nu you can calculate from delta lambda. So somehow, if you know delta lambda, you can calculate delta nu and you can calculate the lifetime. So that is one way of measuring it. Is it clear?
Yes, sir.
Yes, sir.
Okay. Now there is alternative way of measuring this thing. Let's say there are very high resolution spectrometer, like let's say the frequency of the incoming radiation is very high, like a femtosecond spectroscopy measurement. Okay, so the frequency of the incoming laser will be a very intense and very high frequency. Now, usually how there are certain systems where you want to measure the lifetime. So let's say suppose I take a particular material. Okay, So that could be some chemical material, let's some organic compound. So usually you put it in some solution. Okay. And then you actually want, so now as you know, this is so far whatever we talked about, there atomic spectroscopy. So there are atomic energy levels. But let's say we talk about some molecular energy level. So these are similar things. It's just like instead of atoms, we are talking about energy levels which are associated with certain molecules. Okay. So there will be molecular orbitals and there will be transitions, things like that. Okay. So is this part clear what I am mentioned so far? So here also you are trying to know if there is a transition between, let's say, level A to level B or level C, what, let's say if there is a transition between level B and level C, what will be the lifetime that is associated with it. Okay, is it clear? So now what I will
Yes,
do
sir.
is that typically in these experiments, let's say the time stays on the x-axis. So let's say it is second or microsecond or I don't know, millisecond, something like that, a unit of time. And here, let's say this is the population, okay, or something which is proportional to that. Okay, so it could be intensity or something. Okay. Now, usually what happens is that it, let's say I have the certain material within this, and then I heat it with some incoming radiation. Okay, and then I switch it off. So let's say if the frequency of this incoming radiation is very high, or let's say the lifetime is very small, which means that it's just a pulse that I'm applying, and then I'm switching it off. So it's just a instantaneous perturbation that I am applying on the system under investigation. Okay. So if there are, let's say, n number of molecules or atoms, the sum up will go to the higher excited state. Most majority actually will go to the higher excited state, and they will try to come back. And then I want to know what is the lifetime that is associated with it. So if I want to check the population in such case, then usually I will get this kind of graph. So typically I will get a very sharp peak, and then I will see a decay. Now usually this decay happens of the order of this. So there will be a time, or let's say a lifetime factor, or let's say this is the time scale that is associated here, and I'll get this graph, and if I fit it with this equation, then I can easily calculate the value of the lifetime. Does it answer your question?
Yes, sir.
So that is how it is done in experiment. Okay.
So we will see an intensity change in the light.
It actually depends on which quantity your spectrometer is measuring.
Right, sir.
So usually the spectrometer has a detector. So either it detects some radiation or the number of photons or the intensity, something which it measures, which is a representation of the change of population with time. Okay.
Okay, sir.
So I hope this part is clear now. So with this, I'll finish this part. So if you remember that we have started with the 1 electron atom, and I think sorry, this is not 1 electron. Yeah, sorry, 1 electron atom and the fine structure corrections that are arising. So we have done the derivations, and now we have also done some numerical estimations to know what are the different order of magnitude of corrections that are associated with it, and how to measure those things. So is there any question on this? Okay, so if not, then we'll finish this part here. Okay, so we'll go to the next lecture. So in this chapter, we'll be talking about LS and JJ coupling. You all have probably come across this thing earlier in your undergraduate studies, or I think even in quantum mechanics course, probably you have studied this thing, or even, yeah, I think even atomic physics course also you have studied it. So now, what is LS and JJ coupling? So as you know that L stands for orbital angular momentum, S stands for spin angular momentum, and J stands for total angular momentum. Now, before we proceed with this chapter, there are few concepts, or let's say few ideas that we need to first define. The first thing is state. What is a state? So state is something which is usually represented by a certain quantum number. For hydrogen atom, it is the principal quantum number which represents certain state. Okay. It could be some orbitals also, and if there is some energy that is associated with it, so it can represent also a particular state, but that will again be associated with certain quantum numbers. Okay. So anyhow, if there is a state, there has to be certain quantum numbers which have to be associated with it to represent it. The second term which we will be looking at is energy levels. As you know that in a quantum mechanical system, we talk about energy levels instead of a continuum of energy, which means that there are certain energy values which are associated with certain states, and these are some fixed values. They will have, of course, some broadening, but these are at some levels around which this broadening also appears. So these are called as energy levels. Okay. So if we want to know the transition in a particular case, then we want to know from which energy level to what final energy level the transition has happened. So that in that context, the energy level is quite necessary to understand. The third thing is sub-level. So what are sub-levels? Usually, if there is an energy level that is specified by certain quantum numbers, now due to some perturbation, this energy level will be degenerate, which means that this energy level can further be splitted into subsequent energy levels, as we saw earlier. So one simple example could be, let's say I have a spin system. Okay, so I usually like spin systems because this is quite actually close to my heart. So let's say I have a spin system. Very simply, let's say it is an, let's say there are n number of spins. Now they could be either up or down. Okay, and they are just staying like this. There is no external interaction. So in this case, the energy of up and down spin, they will be equal. Now let's say I apply some external magnetic field. In that case, what will happen is that the degeneracy will be lifted, and the energy of the up spin state, or let's say the spins which are having basically up spins, and the down spins, their energy level will no longer be same anymore. Rather, they will be shifted by certain amount, which means that earlier, if this is the energy level where all the up and down spins are staying, now there will be certain splitting in the energy level. So these are called as splitted levels or sub levels. Is this part clear? Anyone?
Yes, sir.
Okay.
Yes, sir.
Yes, sir.
The fourth concept is term. So this term is nothing other than spectroscopic term. So as I explained earlier, that if we are talking about spectroscopy, or mostly it's atomic spectroscopy in this particular case, then each energy level will be specified by certain spectroscopic term. So this is usually specified in the form 2s plus 1 L J. So the values of S, L, and J, they represent, so the combination of S, L, and J uniquely represent one particular energy level. So these are called as spectroscopic term. The fifth concept is the fifth component is configuration. So configuration usually represent electronic configuration. So as you know, for a particular system, let's say if we talk about sodium or potassium or zinc or iron, there is some electronic configuration that puts the electrons in place, and that tells us what are the number of electrons that are keep being put into different electronic orbits. So there are some principal quantum number, and there are sub like atomic orbitals like sp,d,f. So depending on the capacity, how the electrons will be distributed in these energy levels, or let's say these particular cells. So that tells us a complete story about the electronic configuration of a particular material. Okay. The sixth quantity is statistical weight. Here, it is related to the value of L and S. So we'll see later that whenever we are dealing with an energy level, then there will be some L and S associated with it. And further, these levels can have a multiplicity, which means that they can be further splitted into 12 plus 1 term, or let's say there is some degeneracy that is inbuilt in each of these quantum numbers. So let's say for a particular value of L, there are 12 plus 1 values of ml that are possible, or let's say there are for a particular value of S, there are 2s plus 1 values of ms that are possible. Okay, so let's give you a very simple example. Let's say if S equal to 1, then I can have ms will be equal to 1, 0 and minus 1, which means that the total multiplicity will be basically 3. That is we are seeing here 1, 2, 3. Okay. So if we are talking about a particular state that is characterized by one particular value of L and S, then there will be a further 12 plus 1 times 12 plus 1 multiplicity that is inbuilt or inherent in that state. So this is what denotes the statistical weight of that level. So if the value of L and S are large, that means the number of energy levels or let's say the further multiplicity will be quite large for that. That carries a larger weight, which is called a statistical weight. Number 7 is line. So a line is nothing other than whenever there is a transition happening between two energy levels, some spectral line will be appearing or will detect it. So that spectral transition, which is represented by a spectral line, that we call it as line. The last one is called as multiplet. So multiplicity I explained just now. So here multiplet is nothing other than the multiple components that is appearing from a particular energy level, or let's say one particular term. So these are denoted by the term multiplet. So is there any question on each of these terms? So then we'll go to the next part. So let us now talk about a generalized atom which has atomic number of Z, and let's say it has n number of electrons. So you can ask me that why n and Z, they are different. So because if it's an atom, it has to be charge neutral, which means that you can assume that n and Z have to be equal, or the number of electrons and the charge, they have to balance each other. So that is true, but we will take the general case, because in case if we want to look at certain possible specific cases, then it's better to use two different numbers. Okay. So here let's say Z is the atomic number, which means that the nuclear charge that will be present here will be equal to Z times E, and there are n number of electrons. Okay. Now these electrons, there are two types. One is the core electron and other is the optical electron. What are core electrons? So these are the electrons which are usually filled. That means they are staying close to the nucleus, which means that if I want to knock them out, or if I want to take these electrons out of the atomic cell, then you have to spend quite a lot of energy, or the interaction strength have to be quite large. However, there are optical electrons which usually stay on the outer cells, so they can be partially filled also, which means that they are little easier to knock off, or let's say they are available at a lower energy cost if we want to get them. Now, if we look at the Hamiltonian for such a system, then there will be several terms. So the first term will be the kinetic energy term, which is represented by this sum over I equal to 1 to n p I square divided by 2m. So m is the electronic mass, I is the index which runs from 1 to n. So that is the kinetic energy, which is quite general. Now, the second term will be electrostatic energy. So this represents the interaction between electron and nucleus. So it is Coulombic attraction, and we can represent it by the term 1 minus 1 by 4 pi epsilon naught sum over I equal to 1 to n z square divided by Ri. Okay. Then the third term is called as mutual electrostatic energy or residual electrostatic energy. So this represents the repulsion between electron and electron. As electrons have equal charges, or let's say they have same sign of charges, so equal charges will repel. So the Coulomb repulsion between the electrons can be represented by this following term: sum over I equal to 1 to n. Then there is another sum j equals 1 to n minus 1 over 4 pi epsilon naught square divided by Rij, where Rij will be equal to Ri minus Rj. Okay. So these are the three main terms which are involved in this case. Any question? Okay, so the question from my side is why there are two different summations in this third term. Anyone?
So because we are considering interaction terms.
What interaction?
So Rij, where I is a different index and j is a different index.
But interaction we are also considering in part 2 also.
No sir, in that one there is no interaction. Only Ri term is there. So how is, I mean, Ri is not having like any combination.
See, this is also electrostatic energy. This is also electrostatic energy. So the nature of interaction is same in both cases.
So sir, in that one actually there is, I guess, only one electron. In this one, like 2 or more than 2 electrons we are considering.
Which case is there is one electron?
In the second one, I mean, only Ri is given. That means only one. We are talking about only one electron, or I mean, electrons which are not interacting with each other.
Okay. Neil, can you answer this?
Yes, sir. So in the second case, we are considering interaction of nucleus with individual electrons. So the number of terms would depend on the number of electrons. So we have summation over number of electrons. But in the second case, we are considering energy between the two electrons, repulsions. So for each electron, there are n minus 1 possible. If there are n electrons, then for one electron, there are n minus 1 possible interaction terms with other electrons. So we need one index for the electron under consideration and another index for the electrons with which it is going to interact.
Okay. Very good. But do you think this term is correct?
So I think so. There
What you
should
said
be
is,
because
what you said
otherwise.
is correct. Okay. Yes. Repeat. Yes. Continue.
Yes, sir. Because otherwise we would be counting the same interaction twice.
Okay. So what you have to do here?
Add 1 by 2 to the
1 by 2.
summation.
Okay. Good. So is it clear to everyone?
Yes.
Yes.
Yes, sir. So in the first case, we are talking about, so let's say I have one electron here, one electron here, one electron here, one electron here. So the nucleus is unique. Okay, so this is only one. However, the electrons can be 1, 2, 3, 4. So that is why I can only do the sum over all the electrons. However, in the second case, what I'm doing is that the nucleus is not into picture. However, I'm talking about the interaction between this electron and that electron, let's say this and that electron, okay, and this electron. So that is why for each electron there will be, let's say, n minus 1 number of electrons which will be available for interaction. So that is why we are doing one sum that is over I and another sum that is over j. Okay. Okay, so there are actually 3 other types of interactions. So we'll actually discuss in tomorrow's class because they'll take a little bit of more time. Okay, so we'll finish the class here. Any other question? No. Okay then. So we finish the class here. Thank you for your time.
Thank you, sir.
Okay. Okay.
Thank you, sir.
Thank you, sir.
Okay. Okay.